Okay, this talk is titled The Tiny and the Vast, Predictions about Elementary Particles, Dark Matter, and the Cosmos. Next slide. So some of the results we're going to talk about, I'm going to suggest new elementary particles, explain data and effects people associate with the term dark matter, and explain errors in the rate of expansion of the universe. This, of course, is new modeling, and I hope it seems to work. I hope it's correct. Each of these three challenges here has been around for at least 80 years, and I think over the decade that I've worked on them, I've come to realize that it might be fairly difficult to satisfy any one of the challenges without doing at least two and maybe three of them. We'll also talk about some modeling and some other results. Next. That was some links to my website, because we're not going to cover everything here. We're not going to cover the modeling, for example. So for the first challenge, it could be characterized as showing an analog for elementary particles to the periodic table for chemical elements. Next. Okay, so the periodic table, although very familiar, isn't quite what it seems, because in fact, while it has organizing principles like atomic weight and types of chemical reactions, it also doesn't show the actual things that it's talking about. Every one of those boxes I think every one of those boxes has at least one isotope, more than one isotope. So it's actually categories of things. Next. So here are the known elementary particles. We're going to try to extend this to new ones. So next one. And this is a graphic depicting them. So let me spend a little bit of time narrating this. There's a spine, sigma equals 2s. S is the spin, as in s times s plus 1 times h bar squared. That is familiar throughout physics. On the left of the spine, I'm showing subfamilies of elementary particles for which the particles all have positive mass. On the right side, it's ones that have zero charge. There are symmetries and there are not quite symmetries in all of this. So I'll just run through the known and popularly conjectured particles. The zero level there is, the symbols, by the way, are the sigmas and 2s followed by a letter for the family. So 0H is a Higgs boson. There's only one particle there. And 0I is a conjectured particle that might have been prominent during a very early era in the universe called inflation, and people have named the conjectured particle the inflaton. The next line are the fermions. So there are 6 quarks, there are 3 charged leptons, including an electron. And then on the other side of the spine, there are 3 neutrinos. For spin 1, the next row, the 2W subfamily has the Z and W bosons. And the 2U is the 8 gluons. And then the 2G is the photon. People have conjectured that there ought to be a graviton. That would be in the 4G place there. And a little bit of organizing. The ones in the 2 columns that say anhadron-like in today's universe are only seen bound together. So quarks plus gluons is basically where those particles are seen, and they're called hadrons, like protons and so forth. Next. I actually repeated that slide here because I just want to make the point that below the main part of the slide, there is a caption, a lot of caption material. And if you do come back and find this on YouTube, then stop with the slide. You'll know what's going on there. The explanations are sort of there. So this is where my modeling gets us to. It actually does output solutions that are to equations. And the solutions Some of them associate with all the known elementary particles. One solution associates with the what I call I boson. It's a perfect candidate for the inflaton. In the fermion line there are some new particles that I conjecture. I call them arcs. That's kind of a verbal play on the word quark, because if you take the Q out of quark, or in this case, you imagine quark-like particles that have no charge, that's what I'm talking about. And then there's a new thing there, the spin 1 so-called J boson, and that actually may be something that would explain something called Pauli repulsion, or the Pauli exclusion force, that's supposed to be part of the residual strong interaction, or the Pauli exclusion force pertains to identical fermions of any type, including non-elementary particles. So in this modeling, it actually turns into a boson. And then my solutions also go with the graviton over there, 4G, a spin 3, and a spin 4 similar zero mass particle. Next. Okay, we will come back and see some of that modeling later. So another challenge is to describe dark matter. Go. And this is a little graphic that shows a couple of galaxies. And we could conjecture that dark matter is nothing more than those arc particles married up with gluons. Perfect candidate for dark matter. No charge, wouldn't interact with light, everyone would be happy. But we're starting to see in data patterns that show seemingly prevalent ratios of dark matter to ordinary matter, and just having those hadron-like particles consisting of arcs and gluons probably wouldn't be able to explain that data. Next. Okay, so here are some of those ratios. And the long known one is density of the universe, sort of how much dark matter in the universe compared to ordinary matter. 5+1 has been measured quite some time ago, and it stays there. Some newer observations have to do with galaxy clusters and some absorption of cosmic microwave background radiation. We'll come back to all of these later. And then some observations about galaxies, 0+1, 4:1, and 1:0+. So arcs and gluons wouldn't get these ratios, but what I'm proposing does. Next. So what I think happens here is that aside from those G family elementary particles, like the photon and the graviton, there's a notion of isomers. And what this means is that for all those other particles, we're going to think of there being 6 isomers of every particle. One of those isomers associates with ordinary matter, but the arcs and gluons with that isomer don't, or the arc hadron-like particles don't. For the other 5 isomers, everything associates with dark matter. And part of the reasoning here is that each of those isomers has its own somewhat analog to the photon. It's not quite as strong an analog as you might think, but the primary things that go with the photon are replicated. And so we wouldn't see very well matter related to the other isomers. It will turn out that one instance of gravitons spans all 6 isomers, whereas approximately each isomer has its own photon. These are both approximate statements. And so that gets us into pretty good shape. It turns out also, for reasons I might mention later, 4 of those dark matter isomers are sufficiently different from the ordinary matter isomer that they would evolve very quickly into cold dark matter, which is a requirement if this is all going to work and fit with known or assumed modeling. And I guess at this point, let's go on to the next slide. So here's a graphic that just sort of depicts what's going on. The so-called isomer zero, the blue stuff, that's what we see and are familiar with. The arcs and gluons are that black rectangle over there. This is density of the universe kind of broken up into pieces. Each of the 6 isomers has arcs plus gluons, its own. And then you see the other 5 bars there of major components of dark matter isomers. And the notion that maybe isomer 3 evolves somewhat similarly to isomer 0, which is familiar ordinary matter. Okay, so that's a depiction of where we get to 5 plus to 1. The plus is basically the bar or the column of black stuff there. Okay, next. And the 5 is the other part of it. Okay, so I'm going to talk a little bit about modeling, not in much detail, and then we'll show some results that underlie such things as dark matter, and also the third challenge, which we haven't talked about yet, which is explaining eras and the rate of expansion of the universe. So cosmology, really large-scale stuff. So next slide. Okay, so just a couple of words about the modeling. Much of physics over centuries has been modeling that deals with motion and changes, motions of and changes to objects. They accelerate, they decelerate, they change state. And much of that modeling has roots in mathematics of continuous functions, leads to something called the principle of stationary action, and very much a lot of familiar physics. It turns out that the modeling that I'm adding actually doesn't do that at all. It's actually associated with integer arithmetic. It's all quantum. In effect, we're doing discrete things like not very many elementary particles. They have discrete properties. And so we bypass even the idea of having to go through the century of extant modeling that went from classical to quantum. We are starting with something that looks very quantum at the beginning. Okay, next. So one key idea that got me into this and dates way before the 10 years that I've been working on this thing is an idea that in extant modeling for photons, one thinks about a left circular polarized mode and a right circular polarized mode. The excitations are each represented, for each mode are represented by a harmonic oscillator, and life is very pleasant. But at the same time, the same physics says, well, instead of 2 dimensions, we tend to think of the universe as being modeled in 4 dimensions. So instead of 2 transverse modes or circular polarized modes, why don't we have a third oscillator about longitudinal polarization? And most physicists would say, stop there, doesn't work, photons have no mass, and I agree. But if you actually put in a harmonic oscillator there and give it mathematically an excitation ground state that has a quantum number of -1, then it turns out the raising operator never raises, and so you now have a nice representation for the spatial parts of 2 modes. And then on the temporal side, you can have one oscillator that starts with a ground state, and now you have a very different pair of representations for 2 modes, and there's a balance between the sum on the left side and the sum on the right side. In either case, the ground states add up to 1/2. These are energies, standard statements about harmonic oscillators. And what's going on the right-hand side is you've got 1/2, you've got -1 plus 1/2, 0 plus 1/2, 0 plus 1/2, and you get, as a ground state, 0 plus 1/2, and it matches the other side. So that was a root for this. I'm actually phasing the root out in work that I'm doing will make this a little bit easier to understand for people in the next iteration. Next slide. Okay, so this is something that comes out of this, and if one keeps going with what I've been talking about or the newer basis, easier to explain basis, then one winds up getting a model that has components for electromagnetism and components for gravity. And this might not be much of a surprise if you think of Maxwell's equations or charge current 4 vectors. Then you're already starting to do components for electromagnetism. So here, if you think of an object, then the 2G.
Excuse me, please. Just a moment. So this link is going to expire in a moment, and so we have created one new link. Sir, I have emailed you the new link. You can join.
Oh, so everybody has to rejoin?
Yes, on the new link.
All right, so give your explanation, and I will rejoin as I go here.
Yes.
Amal? Hello, Amal?
Let's wait a moment. I think we had 50 plus people. So, and again, for people who are logging back in, I thank you for your
Amal,
patience.
can you hear me?
Yes, please join the new link, everyone.
And your interest.
Yeah, how do I do
And
that?
for taking time out of your
I've
day.
shared the link on the chat box.
Okay.
Now, let's see. All right, good. We're getting another burst of people. Should I wait for about 40 and hope we get that many people back?
Yes, we are getting everybody.
Well, maybe the join rate has ceased at 32. You want to put the slides back up? Okay, well, thank you, almost 40 people, for staying with us at this point. Can you hear me?
Yes, perfect.
Okay. So, we were talking about the idea of breaking up electromagnetism in a manner somewhat similar to Maxwell's equations. And so an object that would contribute to the electromagnetic field, meaning it has active properties. One of those properties would be non-moving charge. We're going to pretend for the moment that things aren't moving anyway. Another one would be a nominal magnetic dipole moment. And it turns out that the solutions that come out of my rather simple math, actually, in fact, you can see part of the math over there. If you look at any one of those so-called components, there is some way to add and subtract the integers to the right of the G in such a way that you get the integer on the left-hand side of the G. So for example, 248, you take 8 minus 4 minus 2, you get 2. And that's a spin 1 component because sigma is twice the spin. And what's going on here is that's a rotating magnetic dipole moment. That the Earth would radiate electromagnetism because of the fact that it has a dipole moment and the axis of the Earth rotation does not match the axis of the dipole moment. So normal physics would pick this up, but in a different way. And so we decompose all this stuff, and for a while it associates without motion, and then there's some more solutions that come in that bring in motion. So for example, the nominal magnetic dipole moment does something, but it doesn't get the magnetic moment that goes with a moving charge. There's another solution there, 2G1416, that does that. The case for gravity is somewhat more interesting, actually. And by the way, the span there column, the column with span in it, that is how many isomers an instance of this solution spans. So for example, the non-moving charge sort of thing, as we'd already advertised, has a span of 1. Each isomer has its own, in effect, charge, or notion of charge. For gravity, it works the other way. 4G4 is Newtonian gravity, 1 over r squared sort of thing. It has a span of 6, and if we didn't get that, we wouldn't be in business at this point. But there are other components that I hypothesize for gravity. For example, if you have a spherically symmetric body in terms of mass distribution, but it rotates, that's the next one there, 4G48. 8 is for rotation throughout this entire chart. And this one only has a span of 2 and actually will be very, very important in explaining a whole bunch of astrophysical and cosmological stuff. The next one down there says that there might be, on a small scale, there'd be another correction. By the way, 4G48, if you're into relativity, general relativity is probably a good proxy for rotational frame dragging. So 4G246 is a correction for non-spherical but not rotating mass. Then there's another one here which we're not going to talk about. And then the two that end in V and W look like rotation for the one that the last one we didn't skip. And one of those is probably rotation around a major axis of inertia. The other one, rotation around a minor axis of inertia. And all of this is producing, in effect, gravitational radiation. There's another solution after that. So this becomes immensely simple, but immensely interesting in terms of what you can do with it. Notice that some of the spans for components of gravity are 1 as opposed to 6 or 2, and that's going to turn out to be important later. Next. Okay, so this just shows, I'm not going to dwell too much on this one. This just shows sets of solutions for essentially all the elementary particles. And it turns out that aside from the G family, which has multiple solutions, as the last 4 rows suggest here, the other subfamilies of elementary particles correlate or associate with solutions that actually solve out to have a 0 in front of the G. For example, the one that goes with the Higgs boson, you can do the math. 8 minus 6 minus 4 plus 2 is 0. And so that's a combination that is going to come out to be something else. And it turns out all of these things, except the last 4 rows there, all are solutions that go to 0. And it turns out that those solutions associate with all the elementary particles that people know, and all of the ones in orange there that my work predicts. So I guess we go on. Oh, a couple of notes. Number one, there's the last orange column on the right is something that comes out of the modeling, and the things that have a 0 there associate with a notion that I would call an object a particle can model as not being interlaced or maybe entangled, is another word, with other particles. On the other hand, things like the I boson, the quarks, and so forth, always model, as far as I can tell, as being interlaced or entangled with other particles. You'll never see them running free under any conditions in the universe, to the extent this modeling is good. Next. Okay, so let's get back into astrophysics, dark matter, and so forth. Next. So here are those ratios that we talked about, and we've already done density of the universe in detail. Galaxy clusters, the hypothesis is they're just big enough and diverse enough that they more or less reflect the densities of the universe, and the few observations I know of do show ratios of 5+1, so we're probably okay there. The absorption of cosmic microwave background radiation is exceedingly interesting. That's a new piece of data within the last few years. And what people did was they looked broadly at cosmic microwave background radiation for the hypothesized phenomenon that hydrogen atoms were absorbing some of that radiation through what are called hyperfine transitions. And it's a very simple experiment, probably very difficult mathematically to digest the data. It was done on a tabletop thing in Australia. Some people in a university in Arizona led the charge on that. And they measured twice as much depletion or absorption as they expected. And a companion paper conjectured, without any substance, that the other half of the absorption might be due to dark matter, but it didn't propose how. My modeling, when I saw that, it just explained it. I didn't predict this, but it explained it, because what we skipped over on the previous slide of 2G68 actually is the right solution there to associate with hyperfine interactions. And it turns out it has a span of 2. So the idea here is that isomer 3 dark matter can absorb ordinary matter, cosmic microwave background radiation, in fact, ordinary matter, almost anything, but not very much or very rapidly. And that explains this ratio. Now, the rest of the ratios here are about ratios of dark matter stuff to ordinary matter stuff in galaxies. And each of those ratios, except maybe one, I think, has been actually observed at least once. I call these seemingly prevalent approximate ratios because I know no others, but there is data, but there's not a lot of data on each of these ratios. So there's an extensive paper on observations of early galaxies. Among a feature of that paper is Galaxies that are sufficiently early as far as when they're emitting the light that's observed, that the so-called redshift is at least 7. And if one looks at the charts in there, it's pretty obvious that what they're saying is that those galaxies at that stage in their evolution have very, very little ordinary matter, or very, very little dark matter. They're all ordinary matter, in effect. That doesn't say that they stay that way, but that says what they looked like at that time. And then there are some observed newer galaxies that also have this ratio. What I think is probably most interesting here is that we're starting to see galaxies with a ratio of about 4:1. And the idea here goes with a galaxy formation scenario that's easy to pull out of my stuff, that says that a galaxy probably started often as a clump formed from one isomer only. And the operative force there was the 4G 246 force, the irregular shape one, which is attractive and has a span of one isomer. So you get one isomer clumps, could be any isomer, and that will drive that will collect stuff. The rotational frame dragging one with a span of 2 will blow away some of the collected isomer and will blow away one other isomer. And then over time, the 4G4 component, which has a span of 6, the normal gravity, will rein in stuff. And so the galaxy will accrue material from a total of 4 isomers. Even if it started with one clump and never collided, then it's on its way to something like 4:1, whether or not it started as an ordinary matter clump or another isomer clump. So that's what's going on there. And then we now know of some dark matter galaxies. Someone's measured the amount of ordinary matter or estimated the amount of ordinary matter in one. And there, because we do see a few stars. And it's something like 1 part in 10,000, I think, 1,000 or 10,000. It's very, very small. So again, this sort of thing would explain something like that. That would be presumably an isomer 3 original clump that blew away all the ordinary matter and then kept evolving from there. So it looks like all dark matter. So we can explain all these numbers, and this gives me a lot of hope that there really is something credible and useful in what I've done. Next. Okay, so now let's turn to really large scale, the expansion of the universe. And people have this notion of the so-called rate of expansion of the universe. I don't particularly think that's as precise a term as it should be. It's really the rate at which neighboring large clumps of stuff drift apart or blow themselves apart, as the case may be. So galaxy clusters and up are candidates for these types of objects. And what's happened is people have started to observe eras in the behavior of how fast those things drift apart from each other. Next slide. Okay, so here's a standard depiction that you see. There's an inflationary era, a very short one, 10 to the minus 30 some odd seconds, maybe not quite at the Big Bang, but very, very short over on the left. And there's rapid, what we call acceleration in the rate of expansion of the universe. Things are moving apart faster and faster and faster. And then after some period of time, you notice the curve starts to bend over. And in the middle, for a period of some billions of years, actually things are still blowing apart from each other, but the rate at which they separate is decreasing. And then the last few billion years, the rate of separation is increasing. And it turns out there's a problem now. People use extant modeling and they underestimate the current rate of expansion of the universe. Next slide, please. So here's a depiction of sort of where the state of the art is. You can see three eras sort of graded by rate of separation there. The inflationary era that we mentioned has a name. The two more recent multi-billion year eras don't have names. And it's thought that most known particles form very early after the inflationary effort, and they form out of electromagnetism, producing pair production, producing fermions and so forth. So this is kind of where the state of the art is. Next slide. This is what my modeling suggests. You'll notice there are a couple of eras before inflation, and what's going on here is very early on, for a very small fraction of a second, there is a span 6 component of gravity that would be most dominant. What happens over time, of course, is as things drift apart, let's say a 1 over r to the 4th type force will eventually dominate over a 1 over r to the 5th force if you wait long enough and things keep going apart. Now, for very small scale stuff like stars and solar systems and so forth, objects transit these eras, neighboring objects transit these eras very, very early, and nobody cares anymore. But for the very large scale stuff, here is sort of a history of the universe. So for a very small fraction of a second, we've got this component of gravity that is collecting something. Just call it energy. It's not clear what that is, but if I'm right, it's collecting stuff. The rate of separation is negative. And at that time, as a small update over here, isomers of that Pauli exclusion force boson and isomers of arcs would form. The isomers of arcs is, I figured that out in the last few months, that would come in that early. And then there is another era. It's actually driven, this slide is not quite correct according to my current thinking. That second era where the rate of separation changes to positive is actually a bounce because of the Pauli repulsion notion and the J bosons. So that's what stops the implosion. And at this point, the inflatons start to form. Then you get the familiar history of the universe that is shown below, except you'll notice that for 3 consecutive eras there, the span per instance of a component of force is 1. But in the current multi-billion year era, the dominant force component, 4G48, has a span of 2. And I'd suggest that that associates with why people are underestimating the current acceleration of the rate of expansion of the universe. Models are probably very much centric to general relativity and then equations of state that are needed for general relativity. And the equations of state would be honed to fit the earlier era, the r to the -4 era, and then would underestimate the effect of interactions between stuff as the so-called dipole force there, our 4G48, takes over. And so actually the dominant thing in some sense is being underestimated by a factor of 2. And the way out of this is just to retune the equation of state to take care of this, I think. But people don't know that they have a problem. They know they have a problem, but they don't know they have a solution like this. And so there's an awful lot of controversy over the last roughly 2 years about this. Next. Okay, some other results that are, I think, of interest. And wow, I'm glad to see people are staying with us. We've held in the above 35 for quite a while. And I hope you stay on for discussion. This is an interesting equation, set of equations, which I've had for a long time. The first equation there, the right-hand side, is the ratio of electrostatic repulsion to gravitational attraction for two electrons. It's independent of the separation of two particles, and there it is. And I use this to define, as you can see, a number that we call beta, and it's a mystery as to why that left-hand side has the expression it does, but let's just leave it there. Let's define a second number, beta prime, which is the mass of the tau elementary particle ratio to the mass of the electron. The tau is another charged lepton in the trio of charged leptons. The tau is the highest mass one. I posited years ago that those two betas are equal. And it turns out over a period of time, this equation has gotten better and better. So at the moment, as we'll see, one way to look at this is which numbers aren't very well known. And it turns out the two numbers that are least well known are the mass of the tau and the gravitational constant. And we'll see this play out in a little while as to how good this equation has turned out to be. But I actually used it in other ways early on too. Beta to the 12th there, the 12 is actually, at least philosophically and mathematically, if not physically, related to the notion of 2 times 6, and the 6 is 6 isomers. So let's go on and see what we got in the next slide. So here, actually, I've done some work that produces a formula that fits the masses of the known elementary fermions. Here I show in the left-hand chart, log 10 ratios, log 10 of the ratio of the mass of the particle it's named to the mass of the electron. So no surprise, 0 for the electron. And you'll notice the table's a little bit of a jumble, but there is a way out of this that makes it look much better. If you take the geometric mean of the two quarks on each row and use that and pretend that it's got a charge of 3/2 the charge of the electron in magnitude, and develop a column there, then you get what you see on the right. And the geometric means do very well. The chart on the right looks perfectly orderly. It's not quite regular. There is some variation in differences as you go up and down each column. But basically, it looks quite nice and it may mean something. So this, it turns out, I'm not going to show you the formula, but the formula can be used to do a number of things. And one can extrapolate from this. By the way, M prime has something to do with charge, and M double prime has something to do with flavor, if you're into fermion physics. If you extrapolate and look for other solutions, it turns out there's one solution that does very nicely for neutrino masses, and there are some others that look like good candidates for masses for our zero charge quarks, known as arcs. Next slide. So here are masses for all of the elementary fermions that people know of or that I suggest. And you'll notice over on the left, the third one down is the tau, the flavor variant from the electron. That is the mass that the formula that I showed you calculates, and the standard deviation comes sailing through, if you do it right, based on the standard deviation of the gravitational constant. This mass and its standard deviation fit within one experimental standard deviation of the tau mass very well. In fact, 8 standard deviations in either direction from this number fit within 1 standard deviation of tau mass. So this looks super attractive, and it doesn't flunk by any means. I show some other masses here, and the arc masses are interesting, but what I'd like to call your attention to in the upper right are the neutrino masses. There are astrophysics data that suggest a range for neutrino masses. And it's roughly, it's about, the sum of the neutrino masses is somewhere between 6 and 12 times 10 to the minus 2 electron volts, if I remember correctly. And one of the numbers that comes out of my extrapolation is 3.4. So you could fit that astrophysics data if all 3 neutrinos had a mass of 3.4 times 10 to the minus 2 electron volts. There are some suggestions based on studies that are supposedly linked to differences in squares of masses for neutrinos that suggest that all the neutrinos, no more than 2 neutrinos can have the same mass. And if that were really the case, then in fact, my solutions point to nice candidate neutrino masses. But I don't think it's appropriate to do that because my work also suggests that you can explain neutrino oscillations and everything else based on the decomposition of gravity and have all 3 masses be that 3.4 times 10 to the minus 2 electron volts. So at least in my somewhat bias, I guess, I think that's probably going to turn out to be a better answer than the mixed mass one. But who's to say? Okay, next. Okay, this is another interesting formula. And this one is almost scary in some sense. There's a better way to present it, but I'll just narrate it here. This is masses for the non-G family elementary bosons. So the Higgs, the Z, the W, basically. And the formula says that not logs of masses now, but squares of masses interrelate. So mass squared is approximately the square of the mass of the Z boson divided by 9. And then times a factor over here. J is an integer, always. S is the square of the spin integer. And Q is the square of the charge expressed in units of the magnitude of the charge of the electron. So here you have something that interrelates, potentially, charge, spin, mass, and some numbers. And it really starts to strongly hint that there are interrelations not only between masses of particles, but between properties of particles. So this one is very, very interesting. And indeed, the number J there couples back to the number of elements in that the piece lambda in some of the solutions. So there's much more, there's even some more coupling than I'm trying to detail here. Next. So here was an attempt, and this is now somewhat obsolete actually, to use the modeling to catalog properties of elementary particles. I now have a much better way to do this, but it does show some interesting features. For example, if you remember that harmonic oscillator that was a switch between mass and no mass for photons, and it turns out the mass branch would be the Z and W bosons, among other things. It turns out that that's a switch for fermions between charge or no charge, and it's a switch for everything else between mass and no mass. So that's somewhere in all of this. Then lambda equals 2, and those gamma expressions associates with charge. lambda equals 4, gravity, and so forth. So stuff like this comes out. As I said, there's a much better way to do this now, and I don't want to belabor this. But it turns out that the series that this shows actually survives. So 2 with charge, 4 with mass, let's call it, 8 with angular momentum, and 16 with momentum. Those are the numbers I just read are all squares. And so that part of the cataloging survives into the newer work. And it starts to suggest now, as I did on the previous slide, that there's something going on that actually interrelates measurable properties independent of the particles that you're measuring or the objects that you're measuring. And then the next line after momentum is that parameter we talked about before about interlacing or entangling and so on. Let's go on from here. Okay, I'm going to briefly just breeze through some other things that people think they need to explain and that my work may explain. So they come in at least 3 chunks: elementary particles and small stuff, aspects larger than galaxies and galaxies. Next slide. So people did recently announce some measurements of energy levels in Positronium. That's an atom-like thing that has 1 electron and 1 antiparticle, a positron. No nuclei, but looks like a hydrogen atom in effect. And I would suggest that if that actually does prove to be a discrepancy point to a discrepancy in extant modeling, probably J boson phenomena can explain it. Very recent observations of something called Pauli crystals for the first time. Those are patterns of fermion stuff. And again, the J boson may help explain that. And then just a comment on the last bullet there. If you go back and look at all my stuff, there's no solution that would point to a particle that has the properties that people would associate with the so-called magnetic monopole. So to the extent that my modeling is accurate and complete, nature would not exhibit so-called magnetic monopoles, which is something people have conjectured about for a long, long time, because there's a slot in Maxwell's equations that could be fulfilled by them, and people continue to look for them. There's no slot for them in my stuff, but who knows? Next. Okay, larger than galaxies. On very large scales, people are starting to report that clumping of stuff is too thin. This is galaxy cluster and larger data. And I think what's going on here, I've already explained to you, is the notion that normal modeling would associate a coverage that's universal for that 4G 4.8 analog to general relativistic rotational frame grating, whereas my modeling gives a span of 2 and therefore a bigger effect. In this case, its stuff repels itself from other parts of the stuff, and so stuff is just too dilute. Now, there's another thing about excessive clumping of dark matter and within galaxy clusters, and I think that there was a reason, which I don't think I have here. Oh, dark matter galaxies might be a source of some of that, because extant modeling wouldn't predict as many dark matter galaxies. Okay, next. Okay, data about galaxies. Very recent paper did some computational work on interactions between neighboring galaxies. And the theme behind the computational work was they were going to explain all the phenomenon they could in one galaxy that would be based on gravitation from neighboring galaxies and see how close they got to observations, and they discovered discrepancies. So I'm going to suggest that I may offer a way out for that, because the notion of isomers and differing spans would put a wrinkle into those calculations that might produce a different result. Galaxies that stopped accruing matter, we've already hinted at something like that. It has something to do with isomers and the notion of this one component of gravity that pushes stuff apart. And then let's see, in the Milky Way, people have found a so-called stellar stream GD1, and they measured it, they've estimated its path to where it is now. It's a bunch of stuff that we can see. And they're pretty certain that the evolution of the motion of this stuff has been influenced by some object of about 10 to the 6th to 10 to the 8th stellar masses. They can't find the object. So maybe it's a dark matter or something, and that would be a kind of obvious conclusion from my stuff. I can't prove it, but at least it looks like I may offer a way out on that one. Okay, next. All right, we are nearing the time for discussion. For those of you wow, the whole 37 people are still here. Okay, so basically we've done what we started out to do. And I would just say that this has, for me, been a very interesting experience, and maybe it works, maybe it will gain traction, we'll have to see. It was very difficult. It's all been done mentally and on paper, no computer aid, except for a spreadsheet occasionally. And maybe it actually offers a way out for things. It also exhibits a lot of reuse of current physics, but in ways that people don't expect. So with that, let me see, I think we have maybe a trailing title slide or something, and we're almost ready for discussion. Next slide. Yes, if you catch this on YouTube, then the video we were supposed to see has been on YouTube for a little while. It was used in a seminar I gave a couple of weeks ago. But at any rate, that's on YouTube, and all that reference, that tiny URL reference, which you may be able to write down, TJBMP, as in Thomas Joel Buckholtz Mathematical Physics, points to my website and to links to that video, to the most recent paper. It'll get updated when I have the newer version, and so forth. With that, I think we're on to a trailing title slide. And so it is time for questions. And I am willing to stay as long as people are, never mind that it's almost 1 a.m. here. And fair game on this is anything related to physics. And if it's some interest, since you had a little bit of introduction to my career, something like that. There are a lot of topics that I, like science and religion, that I do not want to cover.
Thank you very much, sir, for the interesting talk. If anyone has some questions, they can just unmute and they can ask the question.
Can I ask?
Go, yeah.
Yes, sir. Like I've recently read the news, and I found that we have actually found a new type of matter called the electron quadruplets, right? So can you please throw some light on it?
Could I ask you to somehow point me to that? I am not familiar with it at all. Let me make a slight comment. You might, Amal, if people put things in the chat, would you be willing to scrape the chat at the end of this and save it? I hope you will. anyway, if you can somehow communicate that, something about that paper to me, I would love to look at it. I am not familiar with it. Let me
Yes, sir.
say that, let me put in a little bit of commentary about my situation. It is now somewhat more than 50 years since I got my PhD. Most of my career was not in physics. I've reconnected a little bit with the field, especially after joining the Ronin Institute. There are some other physicists in there, but my source of information, which I'm very thankful for, a lot of the information has been science journalists who write about new discoveries and who write about new theories. So if you can maybe point me to an article or a science journalist coverage of this, it'll be appreciated. I will take a look at it. If you include your name and contact information
Yes, sir.
in wherever, then I will try to get back to you and see if I can figure out anything that is meaningful to say.
I'll share that in the chat box. Yeah, the article like which points it to the one I've said. I'll share it in a minute.
Okay, Amal, please, at the end of this, scrape the chat box if you would.
Yes.
Okay, and save it and send it to me somehow. Okay, somebody else? Don't be shy. There are no bad questions. There's been a lot of stuff here. You have varying degrees, I assume, of familiarity with it. Some of you maybe are just curious but not familiar with any of the topic at all. Some of you may actually be doing work in some of these areas. I don't know. But there are no bad questions as far as I know.
So I have one. It's not a specific, but a general one.
Yeah.
Like, so during the research, like every time, there's a hurdle and we try to give up. Like, was there anything that kept you going? Like, would you motivate us on that? Like, we often go dilemmatic, in searching our passion towards science, and then we stumble. Like, would you like to put some motivation? Like, what was yours, and how can we try the track?
Okay. I think this is an excellent question. It is, of course, the answer is personal for me and does not necessarily apply, but maybe there's something people can get out of this. It turns out that I kept physics as a hobby after I left the field. The last day I formally had a paycheck or did something formal in physics was, I think, the beginning of 1977 at the Lawrence Livermore National Laboratory, where I'd been an employee or a consultant off and on for a number of years, actually, starting before I got my PhD. In fact, my PhD research was done with a scientist out there. But I had a good career. Every once in a while, I would think about maybe something wasn't quite as good as it should have been in physics. And while I did not in graduate school or in that subsequent time, partly at Livermore, come up with something I was passionate about. Somehow when I got out of graduate school, I just wasn't passionate about physics the way I had been when I came out of Caltech, starting into graduate school. And by the way, it's partly me and it's partly circumstance change. The US had gone into the Vietnam War, and actually job opportunities in industry as well as academia for physicists were not very good. Physics had built up before the Vietnam War extensively in academia and probably overbuilt slightly. At any rate, so I just kind of kept going. And for example, that idea about 4 dimensions and 4 oscillators and photons came up somewhere along the line. It seemed to make sense. And some other things came up. But a catalyzing event was about 10 years ago now. And that was that my wife and I went to a UC Berkeley outreach program. We live here in Silicon Valley, which is not that far from UC Berkeley. We're actually neighbors of Stanford University. We're very lucky for where we live. It's a center for much stuff going on in the world, in science and engineering and biotech, in academia and so on. 2 premier universities within driving distance of here. And actually 3, because the University of San Francisco Medical School, University of California, San Francisco Medical School is very highly ranked also. At any rate, so Berkeley had an outreach program in a home in a neighboring town here. And the speaker was a fairly well-known astronomer who actually turns out is now a distinguished graduate of Caltech. The Alumni Association gave him a Distinguished Alumni Award. And he gave a talk on eras and on the rate of expansion of the universe. He actually was on both teams that led to the data and the discovery there about the rate of expansion of the universe, that it is accelerating. They didn't work on how fast, but they got it right generally. And the leadership for the 2 teams shared a Nobel Prize for that discovery. But this particular physicist was on both teams and somehow didn't share the Nobel Prize. Anyway, he gave this talk, and he basically went through that slide that I showed and other things about the large-scale universe. And I came away with an idea, well, maybe there ought to be some very easy notion of how that works. And I started to play around with the idea of sort of 2 photons might be a graviton. That sort of got phased out. Now it's come back a little bit. Some spirit of that sort of thing, with the idea of multiple interactions back and forth between the objects. Very hazy recollections at the moment. But I kept on going, and eventually it started to look like the multipole expansion for gravity meant something. And I for a long time, had the idea right, but the expression wrong, and a whole bunch of other stuff went on. But basically, and by the way, the 4-to-3 ratio that was in that equation that defined beta comes from that era for strange reasons. So at any rate, somewhere I was latching onto something, and I was started into an exercise that I would call applying big data techniques mentally, not through computers or artificial intelligence or neural networking. Big data techniques applied mentally to a very small data set, because I wasn't dealing with an awful lot of data. I'm still not dealing with an awful lot of data. And there's danger there, because as I kind of knew ahead of time, and now I've come to discover, I think, more. If you play around with math long enough, you can find a way to fit almost anything. And in the case of the problem I'm doing, there are probably too many fits. Some of them don't seem to have produced results that have gone very far. String theory may be producing results in other directions, but not for what it was originally invented, which was some of the problems that I may offer some insight about. But so part of the problem was just weeding out, shall we say, the stuff that wasn't going to be useful later, and at the same time coming back to older notions that I'd weeded out in newer contexts. So it was a very difficult problem, but I kept with it, and fortunately I had the circumstances for which I could turn this into full-time self-employment with no pay. And that's what I did. So I've been at this very steadily for 10 years. All right, let's move on to something else or ask another subtlety.
Yeah, that was really nice. Thank you.
Thank you.
That
Okay.
nice. Thank you for all the inspiration. It was a
Yes,
nice.
just keep at it. If you have the circumstances and the passion for it,
Yes,
who
sir.
knows what you can do.
Yes, sir, exactly. That was so motivating. Thank you so much.
Somebody else? Something?
Hello, sir. Hello, sir.
Yes.
Yes, sir. I want to ask about electron positron annihilation.
Yes.
Electron positron and basically matter and antimatter annihilation. Where does all the mass is gone and we find a pure form of energy?
Electron these are areas which I'm not totally up to date on, but at least in this case, I think most of those annihilations produce photons. And that's it. The energy goes off in the form of photons. So there are some conservation laws. For example, conservation of charge, but charge goes from +1 plus -1 to 0, and so forth. But basically, it goes off in the form of photons, and if you're into this sort of stuff, sort of the equivalence, ideas of equivalence between mass and energy that underlie some of Einstein's work in relativity.
Thank you, sir. Thank you so much, sir.
So thank you, everyone. We cannot take any more questions now because it's already too late. And Thomas sir is also having.
Oh, I'm fine if you want to get another link.
So we'll be taking all the questions via email, and we'll try to communicate it to you later.
Okay, that's good too.
Yeah.
Well, I'd like to thank everybody for attending and for 30 some odd people staying with something under somewhat technically trying circumstances. A double thank you. And of course, for the people, some of whom I don't really know, who probably collaborated to make this all possible.
Thank you so much, sir, for the talk and staying up. And we'd like to thank everybody. This talk was organized by Olympia Academia, and you can visit the website for more details.